right, welcome back to Big Data Beer Drinking with Ted Dunning. Ted, can you introduce yourself, a little bit of your history and what you're doing right now?
Pretty easy to do. I'm Ted Dunning. I work for MapR. I have to point, I found out, because nobody ever sees hats anymore. They're just part of the landscape.
Of the ADD.
So, yeah, I don't know what it is. I think maybe people have put brands on things too long.
Yeah.
Nobody sees anything anymore. But I work for MapR. I'm chief application architect there, which means I get to go talk to people about what they're doing with big data and try to figure out cool ways of doing things, figure out new things we can do, and exciting ways to use big data tools.
So you did a lot of really cool open source stuff. Can you touch a little bit on this?
Actually, I'm a case study for a guy who hasn't done as much code. I tend to work on the code too long, make it too tight, but I certainly say too much on the mailing lists.
I think you won the person with the most responses in the Hadoop mailing list for a few years in a row, right?
That's really embarrassing. Yeah, even years after I kind of toned down the Hadoop mailing list and moved on to Kata and then to Mahout and then other projects, it still kept coming back up. Apparently I sent a lot of email in those years.
Yeah.
My real contribution, I think, though, and appropriate for today, is that I bought the beer at the first Hadoop users group. Would you like a beer?
Oh, yeah, I take a beer. All right. And it was that kind of beer?
Yeah, well, no, it wasn't this type. Well, there was a little bit, but now this is techno beer.
So what is techno beer?
It has a special technology inside it called a widget.
Okay.
That helps make it feel like a pumped beer from Northern England.
Oh, interesting. Yeah.
And there's physics going on there. See the bubbles going down?
Yeah.
Yeah, that's because it's a conical glass.
Mm.
That was published in Science, I think, a year and a half ago. They finally analyzed why Guinness bubbles go down.
Uh-huh. Because of the glasses.
Yeah. But anyway, Boddington's from Northern England, where I did my doctorate.
Okay. What do you wrote your doctorate in?
On computers, yeah. Who would guess? And statistics and data mining and genomics and language. You got the good one. This one's the dangerous one. Oh, well. Just a little bit of beer in the carpet. Makes it authentic, right?
Exactly.
But yeah, it was a statistical test. This was before big data was big.
Mm-hmm.
It was back when a gigabyte was a really lot of data.
Yeah.
And IBM was famous for analyzing 1 billion words of text.
Wow.
But it was a statistical test that embodied in a very simple form a way to find out what's interesting and what's coincidence. Mm-hmm. The world's just full of gratuitous coincidence, but it's also full of structure.
Yeah.
And so this was a very, very simple way to find structure. And it was very exciting because we were able to, it was one of the first studies to find certain kinds of structure in genomes. And certainly we found some very cool stuff in text. And we're able to build text classifiers very efficiently. Prost.
Cheers. Prost.
Cheers. And it's called bitters, but it's just anything but, isn't it? Very smooth.
Yeah, I'm glad. I'm not into the American pale ales, so.
Some of those are bitter, nasty. But anyway, these techniques have stood the test of time. That original paper that I wrote in '91 has been cited 1,500 times now, and
wow.
I've used it over and over again. A bunch of people have tested it. It's the most effective, simple piece of code I've ever seen. 10 lines of code that really, really make a lot of things easier to do.
And is it about what's the magic or the secret sauce in it?
Don't make assumptions.
Yeah. Okay.
Yeah. So a lot of the statistics were designed for paper and pencil. Mm-hmm. And this is true all through statistical analysis, is that they were largely invented with different constraints than we have now. Even if they were done in the era of computing, they were done with different computers than we have now. Mm-hmm. And so this went back to the drawing board and said, wait a minute, what are we trying to do? Mm-hmm. And in that case, we're just trying to find interesting coincidences or real structure. Mm-hmm. And it went back, removed some assumptions, like a normal distribution assumption, And the result was much better results, especially in the small count case. And small counts are where everything is because of the long tail.
Yeah.
And so we were able to find interesting structure, throw away the dross, build all kinds of fun systems. And even now, some of the exciting stuff that I do is on recommenders based on this test. It's just, again, very hard to beat. Only in the last few years have really practical techniques on a scale become available to beat this very, very simple technique.
So you did a lot of work on feature reduction, if I'm not mistaken. Do you want to double click a little bit more on this? What over the years, the secret sauces and the findings?
Well, again, it's the same secret sauce.
Okay.
It's eliminating accidental coincidence from things. And so you set a lot of things to zero. Now you only solve for the interesting variables, the interesting interactions and so on. And the problem's much easier. And lately, there's new techniques. There's something called lasso that's really exciting about the way it can induce sparsity, but in a much more principled way, in a much more global way, where you can trade off which one you want to pay attention to. It doesn't actually eliminate variables. It just sets a lot of them to zero.
Okay.
And it has relationships to sparse techniques of all sorts.
And the reason you're setting that into zero is basically just to increase the signal in the interesting areas.
And to not give too much weight to gratuitous accidental things that have happened.
Yeah. Okay.
When you have millions and millions of variables, shit happens.
Yeah.
And accidents happen.
Yeah. So you talked a little bit about recommenders. So you did a lot of work on Mahout. What is the interesting new stuff there in general and implemented in Hadoop, Mahout, that runs on Hadoop that excites you?
Well, one of the things that is kind of an odd new thing that comes out about Mahout is the number of companies that are actually using it. Over and over again, I was just talking to a guy from Barclays, it's a bank, and not that this is a specific endorsement of it, but he was saying what amazing techniques. And in order to impress me, he said he used Mahout recommenders. He didn't know that I was a Mahout kind of guy.
Yeah.
And so just every day you hear about somebody else who uses Mahout's recommenders, partly because they're so simple.
Yeah.
The on-ramp is small. It passes the 45-minute test.
Yeah.
45
getting
minutes.
something done in 45 minutes?
Yeah, because otherwise it's too complicated, too weird. I don't have time today.
Right.
And even if it has huge value that might take months and months of work to prove out,
Yeah.
if you can't see something in
Right.
45 minutes, people just move on.
But I think that's one of the secrets of the more successful open source projects recently, getting something done very, very quickly, right? That brings us back to ADD and kind of the information overload everybody has.
Yeah, and it's not even really ADD. It's an enforced evolutionary selection because there's too much to think about.
That.
Yeah.
If you get 100 emails a day, if you subscribe any reasonable mailing list, right, then you just have to.
Well, and like the joke video goes about Mongo being web scale, frankly, that's not what's successful about it. The success is you can install it easily.
Right.
In fact, I just put Postgres on my laptop. It's beautiful.
Yeah, simple.
Double
fast.
click, drag, Postgres.
Yeah, sounds like you have a Mac.
I have a Mac. I love easy.
Yeah, me too.
But it's that experience, that simplicity that really, really drives people to want to invest the extra time to find the real value.
Yeah. Let's come back to the recommenders. What are the kind of use cases you see people using?
Recommenders are just amazingly ubiquitous lately. A friend of mine, Mahout co-contributor Robin O'Neill, just recently showed me that the new Google Maps is almost entirely based on recommenders. There's way, way too much stuff to show on any map.
Yeah.
There's a massive amount of stuff. You wouldn't be able to read it. And so what it does is based on what you've done lately, what you've clicked on, what you've typed in, it selects which things it wants to show you. So I do this actually now in my talks. I show what happens if I search for a restaurant by name near our office. And it shows all these restaurants in the same price range, roughly the same cuisine or stuff. Then I search for the MapR offices. All the restaurants go away, and all these high-tech offices around MapR show up. It knows which sort of thing I'm doing. And in fact, the demo used to work better because now it knows that I search for restaurants in that neighborhood. So it starts showing.
It mixes the technology with the restaurants.
That's right, and so it's learned already some aspects of what I like, and there are many things that it does. It'll de-emphasize roads if you're a bicyclist or you're on mass transit, and countervailing approaches will be done to different scales. It might show you more roads.
Is there a data privacy issue with this?
There are data privacy issues everywhere.
Yeah.
And people really don't recognize how ubiquitous they are. Google has a pretty darn good track record, and they've taken a lot of efforts. So ultimately, just like search histories, those are sensitive. And even though they're not legally sensitive, Google is doing the right thing by treating them as very sensitive and being pretty careful. We've used Google as a partner with the Google Compute Engine, and I've been very impressed. For instance, the disks that you get on the virtual instances are encrypted by default. In fact, I don't know how to defeat that.
Yeah.
And so if you just do a toy example, the data at rest is encrypted.
Yeah.
And maybe you should do a better key management so it's always changing or whatever, but at least the zero state, the simplest case, is done well.
Yeah.
So yeah, I think that there's always issues about privacy. There are really subtle things you can do with big data, which is the whole value.
Yeah.
But those things can also be used to invade privacy.
Yeah. Let's switch topics here a little bit. You told me a trick how you identify German developers, like all over the world.
It's not just developers, but Germans.
Like
yeah.
general Germans?
And in honor of that, you see, I wore my sandals with my socks on.
Yeah.
And I don't know what it is, but for the last 30 years, I've noticed that Germans in warm climates wear sandals with socks on. Turns out, I think wearing socks with sandals works really well because then you don't get the sand scraping your skin away.
That must be a
and maybe also, there's got to be an optimization principle.
Yeah.
This is Germans after all, and we have stereotypes to fulfill and so on. Maybe it's just because if you live in a cold climate and you want to wear sandals, it's cold.
Yeah.
And you want to wear socks.
Yeah, you'll get used to it, right?
Yeah.
What excites you most about MapR technology?
Well, MapR has some really exciting technology that's implemented by these amazing engineers that we have. But one of the nicest things is it pushes down a lot of the complexity and a lot of the considerations that have plagued Hadoop over the years into kind of the noise level down below the level of perception so that people can focus on where they get value. That's at the application level. Actually, where Datamir lives is where the major value is going to be in big data. And at the platform level, it's really important to do all of the things right that people should be doing right anyway. That's replication, that's survival, that's HA, that's performance. All of those things should not be at the application level because then every application as a silo will have to re-replicate those implementations. And so MapR has been able to do that and do that in a way with an architecture that keeps on giving. Good architecture you do once, and then next thing is easy, and the next thing is easy. And so MapR tables are a good example of that, where it's a re-implementation of the HBase API with stunning performance and some real functionality advantages due to the fact that it's down in the file system rather than as a separate layer. So every time you have moving pieces, things are hard, things are complicated. And when things get complicated, they get wrong. Just inherently. I mean, operationally, if not done initially. It's extremely hard to do coordinated parallel systems. And by pushing it down into the file system, you eliminate 4 or 5 systems from the game. You have the client and you have the server, and that's it. So it's much simpler. That leads to higher performance, higher reliability, simpler failure scenarios, and of course, getting something to work well is much easier than getting it to fail well. And
Well, and you should fail fast, right?
you should fail fast, you should fail safely,
Right.
you should fail reasonably,
Mm-hmm.
and you should provide good feedback. And those are very hard to do because the more systems you have, the system, the obvious complexity goes up exponentially because you have n things that could be working or not. So you have 2 to the nth scenarios just to begin with, even if you don't consider time. And there's time now. So you have all of the possible orderings of 2 to the nth possibilities. And it's just absurd. You can't think about that by enumerating cases, by enumerating tests. You have to design that in. And that's where architecture is. Yeah.
Okay. What's your recently most fun GitHub or Salesforce project you're hanging out with? And tell us a little bit. Feel free to use the chalkboard, of course, as your or cool new technology you're looking into. Something on the edge that really interests you.
Yeah, it's hard to say because there's so many cool things on GitHub and stuff. I actually found 2 projects on SourceForge today that I thought were cool. Yeah. Which is amazing because it's so stylish to be on GitHub. Everybody's moving over.
Yeah.
But what it was is I was looking. It's a strange story, but I was looking for jet turbine simulators.
Okay.
Just as one does.
Sure.
The reason I was looking for that is I wanted to have something that would produce a very good anomaly detection demo. Mm-hmm. And you can do anomaly detection by frequency of events. Did we get enough sales? All the Web 2.0 kind of anomalies you can have. Yeah. People start talking about something different, sentiment goes bad, Twitter goes evil, whatever. Right. All of those things are obvious anomaly detections, but I wanted a physics one.
Okay.
So I really wanted to find a good turbine simulator. Oh, these things are complicated. Yeah. So I wound up looking at how turbines work, and I'm going, whoa, that's more complicated than I thought. Yeah. And so I haven't found a good one yet. But the best ones I found were from Technische Universität München. Oh, and then another one that I don't know who it was from, another student group, actually. But my God, these turbines are complicated, amazingly complicated, and lots of ways to fail.
Did you ever play around with NetLingo? Like a multi-agent simulation engine?
Yeah. I've done a lot of simulation, mostly continuous simulation, but some discrete event simulation. I did some of that when I first came to MapR, because again, failure scenarios. Right. Very hard to compute, very hard to find expected values. What is it? Probability of failure. What's the probability of failure that will be bad? Yeah. So I've done a fair bit of those. Those can be really fun, and you compute probability of failure 3 hours or 3 millennia, and you can actually simulate. Run the system for 1,000 years, 500 times. Right. It's kind of cool, and it's fun to watch these systems run.
And did you integrate this in the unit test framework then, or
no? This was a theoretical. Okay. So the question comes up. There's very subtle questions of how long do you make a disk stripe? Right. And at least with very pessimistic considerations of disk failure rates, a disk stripe of 4 can lead to 1,000 years or more average time to data loss. A stripe length of 10 or more can lead to a 50-year or less average time to data loss, which is unacceptable. Right. So because it's a double exponential, and so you have these horrific threshold effects. And the problem is, if you have a disk failure, it takes a while to recover it. Right. You could have another disk failure. It takes a while to recover that. Yeah. And then you could have another disk failure. Could happen when you have 10,000 disks.
Well, I wonder if anybody else ever did any research in that area to configure Hadoop correctly and all the underlying things, right?
I don't know if they did or not. And if anybody did, I think it was Google who did it originally in their first paper. Because I found that most of the assumptions, especially if you assume late 90s technology, most of the assumptions are really quite good that underlie Hadoop. And of course, those all go back to the Google file system paper. Yeah. And so I think that there's more analysis in there than most people have done. Yeah. And it's only when you really start striping the disks so that one failure causes the need to replicate 5 disks or 10 disks, that you have long enough failure recovery times to start seeing these effects. So I suspect, because Google tends to overanalyze everything, they can do it. They've got the people, they've got the time, they've got the advantage.
Yeah.
I suspect that somebody there did do the analysis.
What are now that we are at this really interesting low-level stuff, right? And when we met over drinks, we had quite some conversations about the interesting low-level things that, kind of lead itself to different architecture, not just on the infrastructure layers, and also on the application layer. What are the things that, now that Hadoop becomes so popular, and a lot of people don't even actually know all the underlayings and how it works, and they want to have real-time SQL on top of a sequential file. What are the kind of things that, as we really down here, you think that people really need to understand to make good decisions up here?
I would put it the other way.
Okay.
Just exactly the opposite. And I would come to the conclusion that until people forget the details below, Hadoop will not be a success.
Okay.
Until we have a solid abstraction that is predictable and understandable enough, people will not be able to succeed in the general case.
World,
And it's because there's a limited number of people who can spend the time to think at the low level and think at the high level.
Right.
So if you're forced to think at the low level, most people just sink to that level. They're unable to reach high.
Right.
So
I mean, it's the perfect world, right? But
no, it's not just a perfect world. I hate to say it, but I remember a time before Unix file systems, and it was horrible.
Yeah.
Where you either had to specify the length of a file, or you had to specify how it was going to be extended, had to specify where on disk things were. And it was a nightmare.
Yeah.
And it was horrible. And the beginnings of the Unix style happened with a system called RT11, where even though things were still contiguous, you didn't have to specify sizes. And it just handled it. And there was
That's before my time.
Well, yeah. Diese Junge. But it caused an explosion of productivity. And Unix did the same thing. And they did a couple of things there. Not just that you didn't care about the file size or anything like that, but they integrated into the file system an idea of abstraction. Abstraction, of course, is hiding. And so people less and less cared about exactly which sector things were on, exactly which position within a track their sectors were laid out. It used to be people would optimize that they would write, depending on the application, they would write this sector, then they would skip 7 sectors, because that's how long it took to compute before the next sector was ready to write.
Yeah.
People used to optimize at that level. It was crazy.
Yeah. So
nobody does that, and to the benefit of the world.
So then maybe to turn this around, what are the things that, open source Hadoop are missing and we really need to work on to really get to the point that people, one thing that we're seeing every day is that people want to use Hadoop, but then they have expectation like it's a Unix file system rather than,
I have to point out with my hat on, that with some Hadoop distributions, it is like a Unix file system. And in fact, that's one of the exciting things. When we go into a customer and they can start operating with their current codes, parallel, sequential, whatever, it just runs. And now they can do little bit by little bit. They can take a single byte at a time, and they can make the worst problem go away by using Hadoop, which is wondrous when it's right, and it's horrible when it's wrong. So you need to have a mix of tools. But if we go back to that, what does the Hadoop community need to do? It's hard to say a specific thing, because any specific thing is too small. But the real challenge here is that there is a virtue and a defect at the same time. They're always the same thing. Your strength will become your weakness. And the strength of open source is this horde mentality that no obstacles can stand in the way, because it will go around them, and you stop one and 15 will take their place. So the horde going along and self-organizing as needed is a wonderful thing. That's what open source success is built on. At the same time, you have exactly that being the fault of open source. the lack of architectural leadership, and lack of any kind of real leadership.
Right.
And the only kind of leadership available really in open source is to make open source not open source anymore, where people kind of expose the source.
Right.
It's not open, it's not community anymore.
It's like,
it's exposed.
yeah.
I show you what I'm doing because I am so great.
Right.
And you can do leadership in that style. That's originally the Linux style to some degree. He's very open actually about taking contributions. It's kind of the MySQL style. Whatever.
Yeah.
We do what we want. We'll show you. And so the very, very difficult thing for the Hadoop community is to rise above petty considerations and squabbles. Try to come to real consensus, to not waste and duplicate efforts so that the entire Hadoop community can be made larger. And sadly, happily, the Hadoop community has to some extent outgrown just the Apache.
Right.
Now, we can't say that, of course, that Hadoop is any larger than that, because Hadoop is owned as a trademark by Apache, and it is an Apache project, but it is a phenomenon that is much larger now than Apache alone.
Because of the cute logo, I guess.
Well, could be, or the choice of yellow or something. But I think what it is that we now have a much larger, we have a market.
Yeah.
We have a large ecosystem, more than just a few Apache projects, in a way, with values that are very, very different from previous big wins by Apache. Apache itself, the HTTPD, is just so different.
Right. About one observation that I thought was fascinating is Hadoop was the first open source project that created a market, right? So if you think about, whatever, JBus or anything, there was commercial products in that areas before, and then open source, even Unix, right? Then Linux came after the Unix systems, where JBoss kind of almost created this whole, Hadoop created this whole market. And then, let me ask you.
And I think you're right. Not to interrupt. Well, to interrupt. Excuse me. But the open source community is very much built around I could do that better.
Right.
So, over and over again, open source copies. It does not actually invent. It may innovate around the edges, but this revolution happens usually in closed source.
Yeah.
Hadoop is unusual in that there is a closed source thing that open source was able to copy that never went on the market.
Right, exactly.
That's Google.
Right.
And
the interesting thing is it never went on the market. Right?
Yeah. It's the same thing otherwise.
Right. Totally right. What are the most interesting recent books you read? Independent of the fiction books.
Sadly, I don't get to read much fiction anymore. I read vats of articles and a few books. It's frustrating how little I get to read for fun. Philip Jennert's book on data analysis is beautiful. I love beauty in books.
Okay.
And so the classics are always the most beautiful. From Dark Ages, the Donald Knuth books had this beauty to them. And there have been a few others that had that sort of strings, linear algebra, things like that. Mackay's book on information theory, Chris Bishop's book on machine learning. And lately I saw Phil Jennert's book. And one of the things I like about it is that it is very, very approachable, very, very pragmatic, without being at all simple-minded.
Yeah.
It is, here's how we can do these things, practical ways, but exciting problems, but not made stupid. Made easy, but not made stupid. And that's a very, very subtle difference.
Yeah.
I want to show you something that kind of gelled. I don't know who told me the key thing or what, but it comes from the idea of physics.
Okay.
And a phase change.
Okay.
It's why Hadoop is working.
Okay.
Why it's happening.
Go ahead.
So the question is, right now, we have open source happening across many, many industries.
Yeah.
So there's a mystery already. Why everywhere? everywhere at once. Why startups and established companies, finance and physics and electrical industries, all these traditional slow adopters are adopting fast.
Yeah.
All these traditional fast adopters are adopting no faster.
Yeah.
Any argument you make almost that is a threshold, cost, value, things
Yeah.
like that, would have somebody adopting far before everybody else. Everybody's doing big data right now.
Okay.
So there's something wrong.
Okay.
Our mental models are wrong.
Okay.
And I've been thinking about that. And if you draw a graph, first you have to draw a graph, otherwise you don't understand anything, right? And the
All
graph,
about data visualization.
yeah, visualization here, low-tech visualization. If we make size be the horizontal axis, this is small, this is big, and we make value or cost be the vertical axis. So unless you're really an idiot, you look at the most valuable byte first. And so the value goes up initially very steeply. But eventually you run out of most valuable bytes, and so it goes up more and more slowly.
Yeah.
This is just always true. It goes up fast, and then it goes up slow.
Yeah.
It never stops going up because hey, you always learn something.
Yeah.
Okay. And now traditionally, cost does just the opposite. You buy one machine, so you have a non-zero, very small price.
Yeah.
And it's flat for a little while. You just use more of that machine. But then the cost of coordination in traditional systems
Right.
goes up like that.
Right.
Where's the optimum? The optimum is where the slope of these two things is the same. So the net value looks like this.
Yeah.
And because this gets steeper so fast, and because this gets flatter so fast,
Right.
this corner here is the edge of the universe.
Right.
We cannot
For
expand
traditional
it
systems.
for traditional systems.
Yeah.
And it is not a factor of their cost.
Right.
It is a factor of the shape.
Mm-hmm.
Big data systems change that. They scale linearly.
Right.
And that means that the net value does this. And eventually it looks like that.
Mm-hmm.
And this point of the optimum, which is kind of where a bubble would sit, goes out by suddenly 4 orders of magnitude, and we escape the corner.
Right.
All of computer science has been going up this thing,
Right.
going toward the corner. Scalable
And then-
big data computing allows us to escape the corner.
Right.
It's a shape thing. It's a change of shape that's really driving this, not just costs.
Mm-hmm.
And that, in many ways, is the most exciting thing I've seen in a long time about big data, because it explains why we are doing what we're doing. And it explains how we must do things in the future. So the old idea was, say, people talk about denormalization.
Mm-hmm.
They talk about flexible schemas. Why? Because if you don't have a flexible schema, you have accelerating costs. If you ever change your schema,
Exactly.
it's quadratic.
Yeah.
And it's game over.
Yeah.
So you have to have a flexible schema to stay linear. You have to be linear to experience this higher value and higher optimum value. That's cool. I mean, physics is cool, and we never get really cool, simple explanations of what's happening in computing, and this is one of them. And I think that's really why everybody's doing it right now. And I think they're right. I think they smell something has changed,
Right.
so they're jumping on this. So anyway, that's what I think is so damned exciting.
Great. Well, Ted, thank you very much for stopping by and for the drinks. And-
Thank you.
See you soon.
I always like an excuse to drink a good Northern English ale.
Cheers.